titled Characterizing Elliptical Crater Morphologies on the Saturnian Satellites, Updates from, I'm going to pronounce it, Dione.
Yes, that's how I also pronounce it.
Okay, I know some people do Dione.
I don't like Dione.
Then it should be minus as well, because
Yeah.
it's Dione minus
Nope.
and
Nope.
Io.
No.
So without further ado, Sierra's going to talk about Dione.
Thank you. So thank you, Sarah, for the introduction. So today I'm going to be presenting on some of the ongoing work that we have been conducting. So mostly what I'll be talking about has been my portion of the study, but this project includes efforts from Meeting as well as Bethany Furman, who's a grad student at the University of Hawaii now, as well as Alyssa Rhoda. So in keeping with the PCC fashion of presenting on work in progress, the main goal of this talk is to really present what I've been doing to try and characterize the morphology of elliptical craters on these satellites, and sort of get feedback from the community as to potential adjustments I can make to my method if needed, and really just try to make this the most sort of robust data set that I can. And so primarily the way I think about craters in the sense of the Saturn system is sort of tracing back to how did the intermoons form and along what time scales did they form, and sort of how can we then use geology to look at that. So remove the thing. So some of the main information scenarios for these moons start with either potentially all 5 of these inner moons. So when I say inner moons, these are also analogous to the mid-sized moons. So Nemus, Enceladus, Tethys, Dione, and Rhea. So one idea is that these form contemporaneously with Saturn in that same sort of subnebula. Another potential scenario is that these moons form sort of sequentially out from the rings, which would then lead to Rhea being the oldest, and each moon interior to Rhea being slightly younger than Rhea. And if you like giant impacts, I too am a fan of giant impacts. There is also the potential for more recent disruptive collisions causing these satellites to break and then be reaccreted, potentially giving you more sources for planetocentric break. And so, like I mentioned earlier, and thank you, Adine, for the nice introduction to heliocentric and planetocentric material. So I actually don't have to spend as much time on that. So like I mentioned earlier, part of my research focus has been trying to figure out what created these craters, and then how can we use them to examine these potential formation models. So like Adine mentioned, we have 2 main source populations at these satellites, so heliocentric and planetocentric. And previously, myself and others like Michelle have done work comparing crater size frequency distributions to these different sources to try and derive different model ages for these terrains. But this is with a caveat is that these studies rely primarily on circular craters, or assuming some kind of circular diameter for that crater. And I'm sure I don't have to convince anyone in this room that impact craters are an important tried and true method to look at the surface history, since they can often record the conditions in which they form. So for the rest of this talk, I'm primarily going to be focusing on these elliptical craters. So what I have here on the left is this very nice image from CTX on Mars, where it's much higher resolution than anything we have in the outer planets right now. But what you can see is a very nice elliptical shape with one axis here in red, longer than the other. So we have a major axis and a minor axis in blue. And on Mars, you can see this beautiful sort of butterfly ejecta pattern, which we certainly cannot resolve in the Cassini data. And with this crater on Mars, we likely can see this probably came in from the east going towards the west, just looking at where some potential extra excavation happened. And so we define these elliptical craters are typically thought to be formed with either low velocity and or really oblique impacts onto the surface. And for our studies, we have defined elliptical being a crater that has a major axis diameter to minor axis diameter as 1.2 or larger, as to try and remove potential effects from wall slumping or other crater modification. And within the inner solar system, these have also been used to record the direction of impact off the surface. And again, I have to thank Dean for introducing Penelope. Penelope on Tethys is one of our elliptical craters in our Tethys data set. So this is just an example showing how I would have mapped this on Tethys. So we have our major axis and our minor axis. We then measure the orientation of this crater based on the direction that the major axis is pointing. So we measure from 0 degrees north, going clockwise. And we then represent this on a rose diagram, which is useful to say that this impactor could have come from either north to south or south to north, but we can't really fully rule that out yet. And so for some of the previous work we had done that kind of motivated this proposal was looking at these elliptical craters in a global sense across 4 of the mid-sized moons. We excluded Enceladus because of its extensive modification history. And so we wanted to look at the more quote unquote inactive worlds. And so from this, we ended up seeing that primarily at Tethys and Dione, we have a very large east-west trending crater population. And with a little bit of that at Mimas, but not nearly as much. And we're seeing some of that at Rhea, but Rhea and Mimas do not look like Tethys or Dione. And so we have been interpreting this as being representative of a more planetocentric impactor source creating these elliptical craters. And so the overarching question we have for this project is how can we best utilize all of the impact craters for a surface to assess these age relationships? Like I mentioned earlier, these SFDs tend to rely on a circular crater scaling relationship and diameters. And so it's often difficult to include these non-circular craters on SFDs. And so how we're going to get at addressing this is characterizing the non-circular morphology, specifically elliptical, so that the inclusion of these craters on SFDs is more straightforward, and so we can try and get better assessments of the impact conditions and the crater formed in. And so, like I mentioned at the top, this is only one part of a larger project. So we have some additional ISAIL 3D and 2D modeling that has been done and is ongoing, as well as tying it all together. And so what we've done so far is we've utilized the highest possible Cassini ISS NAC images for Mimas, Tethys, Dione, and Rhea. I had 2 overlapping images that included an elliptical crater within it. So on average, these are pixel scales of roughly 200 to 400 meters per pixels. I then generate some elevation models with the AIM stereo pipeline, which then gives you a DEM resolution of roughly 600 meters to 1.2 kilometers per pixel. That's just due to the uncertainties in pixel matching when you're making DEMs. And then we brought these into our Pro to obtain topographic profiles across the crater. So this crater I'm showing right now, this is our example D1. So this is focused on this elliptical crater here on Dione. And in this table, the starred profile, so profile 3 and profile 6, these are indicative of the major and minor axis. So P3 to P3 prime. P3 prime is the major axis, with P6 to P6 prime as the minor axis. And I've plotted all 6 topographic profiles with some offsets so that you can better visualize them. And what we see is, yeah, these shapes are not, it is not a very uniform crater as you would expect if it's elliptical. But what I've started to notice is you do get different diameters, which again is expected. But then when you go to compute your depth to diameter, there's different ways in which you compute this. So you could go by the maximum depth of that within that profile, or you could average that depth. And so I did a bit of both just to see how much it varied or didn't. And there's for some of the craters, or sorry, not craters, for some of the profiles, there is significant variation. And so this is one of my kind of remaining questions, is kind of what do people think as the best way of dealing with the depth, like figuring out that depth from a profile, because unlike the moon, our elevation data is much more coarse, so we can't as easily do a trace of elevation around the crater rim. And so this is just kind of have some videos kind of just showing that in the interactive profile from our Pro. So you can see the wall going down to some anomalous super deep part of hitting the central uplift and then kind of evening out. And this is for, I believe this was profile 1. And then going along P3, which was that major axis, we do again get some local minimum, and then that's again some kind of central-ish maybe uplift, and then with another local minimum, and then heading up to the greater rim. And so on Mimas, however, our DEM is a lot coarser in resolution. So we're focusing on this crater. So this image on the left, this is the image downsample to the DEM resolution. So for those of you familiar, this is the ortho image from this DEM. And so this target crater is 30 kilometers in size, so pretty sizable. But if you look at the two profiles of A and B, it is much less clear where you actually define the rim. Like you can kind of make an argument for it being around here and here for A, but B, it's really unclear. So it's kind of leaving me with this question of how, when you have really coarser with DEM resolutions like this, how do you best go about defining this rim? And so getting to some of these key challenges that we have right now, the other thing I've been thinking about is how do you best separate out this background topography from the main crater signature? Like, is it something like taking an FFT and then getting, yes, thank you, Sarah, and getting the subtracted profile out, and then also combining uncertainties between profiles, because like we talked about today, there are uncertainties in your various measurements. So if I give you an average topographic profile of an elliptical crater, then how do all of these uncertainties add together? And then, like I mentioned earlier, the definition of the floor depth, and then how to report the overall depth diameter of that target crater, because it is varying across the major axis across that crater since it's not circular. And this figure on the right here is just a more zoomed in version of finding these maximum and minimums within a single profile, and this yellow box just, well, not yellow on the screen, but yellow on my screen of where it seems like the background topography sort of starts. Oops. And then this is just the future work. We're continuing with the DEMs and getting these measurements. That Furman's been doing some 2D ISO formation and simulations with the Dean, and then the Dean will be taking those 2Ds and implementing them into 3D ISO simulations of elliptical craters. So I'll go back to my key challenges slide and take any questions or thoughts. Thank you.
All right, so we have 20 seconds before break, but I'm gonna read from the chat after each again. We derived depths from low-res Titan data. It wasn't very sophisticated, but it could be a starting point, and there's a POI link in there to their Icarus paper.
Thank you, Catherine.
In lieu of other questions, because I see Jamie's hand up, but I'm gonna say chair's prerogative. As someone who could potentially be a future reviewer number 2 for something like this, I strongly suggest that you find additional images of the same location and make sure that your measurement of ellipticity is the same under completely different camera geometry.
That's very difficult to do with the Cassini data.
I understand that, but there was a lot of repeat, and some of it was of the elliptical craters. It's a good sanity check that would satisfy a potential reviewer number 2 who would question whether emission angle is skewing you. And I would also caution you with DTMs from the stereo on doing maxima and minima, because those are very noisy.
And that's why I was later taking an average, because I was trying to get a sense for what is looking for the positive data.
With that said, you do have a dimple reminder, but I'm going to say we can go to break, and while we start break, Jamie, if you wanted to ask your question.
Oh, yes, I just was wondering if you could explain to me why a combination of uncertainties between profiles is questionable.
It's not so much that it's questionable as I don't know the best way to do that with these profiles, how to incorporate all these different uncertainties together in making an average topographic profile, because these profiles are not the same sort of, they're not the same lengths, right? Because the data is not circular, so I was just unsure of how to best quantify that and report it.
I have potential ideas
Mhm.
that we can talk about.
Yes, and I'm also talking with Rachel next week as well. Because I've been going to talk with both of you guys about it.
So thank you again, Sierra.